Brought to you by Wikividi Documentaries. Black hole. A black hole is a region of spacetime exhibiting such strong gravitational effects that nothing, not even particles and electromagnetic radiations such as light, can escape from inside it. The theory of general relativity predicts that a sufficiently compact mass can deform spacetime to form a black hole. The boundary of the region from which no escape is possible is called the event horizon. Although the event horizon has an enormous effect on the fate and circumstances of an object crossing it, no locally detectable features appear to be observed. In many ways, a black hole acts like an ideal black body, as it reflects no light. Moreover, quantum field theory in curved spacetime predicts that event horizons emit Hawking radiation with the same spectrum as a black body of a temperature inversely proportional to its mass. This temperature is on the order of billionths of a Kelvin for black holes of stellar mass, making it essentially impossible to observe objects whose gravitational fields are too strong for light to escape. Were first considered in the 18th century by John Michel and Pierre-Simon Laplace. The first modern solution of general relativity that would characterize a black hole was found by Karl Schwarzschild in 1916, although its interpretation as a region of space from which nothing can escape was first published by David Finkelstein in 1958. Black holes were long considered a mathematical curiosity. It was during the 1960s that theoretical work showed they were a generic prediction of general relativity. The discovery of neutron stars sparked interest in gravitationally collapsed compact objects as a possible astrophysical reality. Black holes of stellar mass are expected to form when very massive stars collapse at the end of the life cycle. After a black hole has formed, it can continue to grow by absorbing mass from its surroundings, by absorbing other stars, and merging with other black holes. Supermassive black holes of millions of solar masses may form. There is general consensus that supermassive black holes exist in the centers of most galaxies. Despite its invisible interior, the presence of a black hole can be inferred through its interaction with other matter and with electromagnetic radiation such as visible light. Matter that falls onto a black hole can form an external accretion disk heated by friction, forming some of the brightest objects in the universe. If there are other stars orbiting a black hole, their orbits can be used to determine the black hole's mass and location. Such observations can be used to exclude possible alternatives such as neutron stars. In this way, astronomers have identified numerous stellar black hole candidates in binary systems, and established that the radio source known as Sagittarius A, at the core of our own Milky Way galaxy, contains a supermassive black hole of about 4.3 million solar masses. On the 11th of February 2016, the LIGO collaboration announced the first observation of gravitational waves. Because these waves were generated from a black hole merger, it was the first ever direct detection of a binary black hole merger. On the 15th of June 2016, a second detection of a gravitational wave event from colliding black holes was announced. History. The idea of a body so massive that even light could not escape was briefly proposed by astronomical pioneer John Michel in a letter published in 1783. Mitchell's simplistic calculations assumed that such a body might have the same density as the Sun, and concluded that such a body would form when a star's diameter exceeds the Sun's by a factor of 500, and the surface escape velocity exceeds the usual speed of light. Michel correctly noted that such supermassive but non-radiating bodies might be detectable through their gravitational effects on nearby visible bodies. Scholars of the time were initially excited by the proposal that giant but invisible stars might be hiding in plain view, but enthusiasm dampened when the wave-like nature of light became apparent around the early 19th century. If light were a wave rather than a corpuscle, it became unclear what, if any, influence gravity would have on escaping light waves. In any case, thanks to modern relativity, we now know that Mitchell's picture of a light ray shooting directly out from the surface of a supermassive star, being slowed down by the star's gravity, stopping, and then free-falling back to the star's surface, is fundamentally incorrect. General relativity. In 1915, Albert Einstein developed his theory of general relativity, having earlier shown that gravity does influence light's motion. Only a few months later, Karl Schwarzschild found a solution to the Einstein field equations, which describes the gravitational field of a point mass and a spherical mass. A few months after Schwarzschild, Johannes Drost, a student of Hendrik Lorentz, independently gave the same solution for the point mass, and wrote more extensively about its properties. This solution had a peculiar behavior at what is now called the Schwarzschild radius, where it became singular, meaning that some of the terms in the Einstein equations became infinite. The nature of this surface was not quite understood at the time. In 1924, Arthur Eddington showed that the singularity disappeared after a change of coordinates, although it took until 1933 for Georges Lemaitre to realize that this meant the singularity at the Schwarzschild radius was an unphysical coordinate singularity. Arthur Eddington did however comment on the possibility of a star with mass compressed to the Schwarzschild radius in a 1926 book, noting that Einstein's theory allows us to rule out overly large densities for visible stars like Betelgeuse, because a star of 250 million kilometers radius could not possibly have so high a density as the Sun. Firstly, the force of gravitation would be so great that light would be unable to escape from it, the rays falling back to the star like a stone to the Earth. Secondly, the redshift of the spectral lines would be so great that the spectrum would be shifted out of existence. Thirdly, the mass would produce so much curvature of the spacetime metric that space would close up around the star, leaving us outside. In 1931, Subramanian Chandrasekhar calculated, using special relativity, that a non-rotating body of electron-degenerate matter above a certain limiting mass has no stable solutions. His arguments were opposed by many of his contemporaries like Eddington and Lev Landau, who argued that some yet unknown mechanism would stop the collapse. They were partly correct. A white dwarf slightly more massive than the Chandrasekhar limit will collapse into a neutron star, which is itself stable, because of the Pauli exclusion principle. But in 1939, Robert Oppenheimer and others predicted that neutron stars above approximately would collapse into black holes for the reasons presented by Chandrasekhar, and concluded that no law of physics was likely to intervene and stop at least some stars from collapsing to black holes. Oppenheimer and his co-authors interpreted the singularity at the boundary of the Schwarzschild radius as indicating that this was the boundary of a bubble in which time stopped. This is a valid point of view for external observers, but not for infalling observers. Because of this property, the collapsed stars were called frozen stars, because an outside observer would see the surface of the star frozen in time. at the instant where its collapse takes it inside the Schwarzschild radius. Golden Age. In 1958, David Finkelstein identified the Schwarzschild surface as an event horizon, a perfect unidirectional membrane. Causal influences can cross it in only one direction. This did not strictly contradict Oppenheimer's results but extended them to include the point of view of infalling observers. Finkelstein's solution extended the Schwarzschild solution for the future of observers falling into a black hole. A complete extension had already been found by Martin Kruskal, who was urged to publish it. These results came at the beginning of the golden age of general relativity, which was marked by general relativity and black holes becoming mainstream subjects of research. This process was helped by the discovery of pulsars in 1967, which by 1969 were shown to be rapidly rotating neutron stars. Until that time, neutron stars, like black holes, were regarded as just theoretical curiosities. But the discovery of pulsars showed their physical relevance, and spurred a further interest in all types of compact objects that might be formed by gravitational collapse. In this period, more general black hole solutions were found. In 1963, Roy Kerr found the exact solution for a rotating black hole. 2 years later, Ezra Newman found the axisymmetric solution for a black hole that is both rotating and electrically charged. Through the work of Werner Israel, Brandon Carter, and David Robinson, the Noether theorem emerged, stating that a stationary black hole solution is completely described by the three parameters of the Kerr-Newman metric: mass, angular momentum, and electric charge. At first, it was suspected that the strange features of the black hole solutions were pathological artifacts from the symmetry conditions imposed, and that the singularities would not appear in generic situations. This view was held in particular by Vladimir Belinsky, Isaac Kalatnikov, and Evgeny Lifshitz, who tried to prove that no singularities appear in generic solutions. However, in the late 1960s, Roger Penrose and Stephen Hawking used global techniques to prove that singularities appear generically. Work by James Bardeen, Jacob Bekenstein, Carter, and Hawking in the early 1970s led to the formulation of black hole thermodynamics. These laws describe the behavior of a black hole in close analogy to the laws of thermodynamics, by relating mass to energy, area to entropy, and surface gravity to temperature. The analogy was completed when Hawking, in 1974, showed that quantum field theory predicts that black holes should radiate like a black body, with a temperature proportional to the surface gravity of the black hole. The first use of the term black hole in print was by journalist Anne Ewing in her article Black Holes in Space, dated 18 January 1964, which was a report on a meeting of the American Association for the Advancement of Science. In 1967, a student reportedly suggested the phrase black hole at a lecture by John Wheeler. Wheeler adopted the term for its brevity and advertising value, and it quickly caught on, leading some to credit Wheeler with coining the phrase. Properties and structure. The Noether theorem states that once it achieves a stable condition after formation, a black hole has only three independent physical properties: mass, charge, and angular momentum. Any two black holes that share the same values for these properties, or parameters, are indistinguishable according to classical mechanics. These properties are special, because they are visible from outside a black hole. For example, a charged black hole repels other like charges just like any other charged object. Similarly, the total mass inside a sphere containing a black hole can be found by using the gravitational analog of Gauss' law, the ADM mass, far away from the black hole. Likewise, the angular momentum can be measured from far away using frame dragging by the gravitomagnetic field. When an object falls into a black hole, any information about the shape of the object or distribution of charge on it is evenly distributed along the horizon of the black hole and is lost to outside observers. The behavior of the horizon in this situation is a dissipative system that is closely analogous to that of a conductive stretchy membrane with friction and electrical resistance, the membrane paradigm. This is different from other field theories such as electromagnetism, which do not have any friction or resistivity at the microscopic level, because they are time reversible. Because a black hole eventually achieves a stable state with only 3 parameters, there is no way to avoid losing information about the initial conditions. The gravitational and electric fields of a black hole give very little information about what went in. The information that is lost includes every quantity that cannot be measured far away from the black hole horizon, including approximately conserved quantum numbers such as the total baryon number and lepton number. This behavior is so puzzling that it has been called the black hole information loss paradox. Physical properties. The simplest static black holes have mass but neither electric charge nor angular momentum. These black holes are often referred to as Schwarzschild black holes after Karl Schwarzschild, who discovered this solution in 1916. According to Birkhoff's theorem, it is the only vacuum solution that is spherically symmetric. This means that there is no observable difference between the gravitational field of such a black hole and that of any other spherical object of the same mass. The popular notion of a black hole sucking in everything in its surroundings is therefore only correct near a black hole's horizon, far away. The external gravitational field is identical to that of any other body of the same mass. Solutions describing more general black holes also exist. Non-rotating charged black holes are described by the Reissner-Nordstrom metric, while the Kerr metric describes a non-charged rotating black hole. The most general stationary black hole solution known is the Kerr-Newman metric, which describes a black hole with both charge and angular momentum. While the mass of a black hole can take any positive value, the charge and angular momentum are constrained by the mass. In Planck units, the total electric charge Q and the total angular momentum J are expected to satisfy Q squared plus left squared m squared. For a black hole of mass m, black holes satisfying this inequality are called extremal. Solutions of Einstein's equations that violate this inequality exist, but they do not possess an event horizon. These solutions have so-called naked singularities that can be observed from the outside, and hence are deemed unphysical. The cosmic censorship hypothesis rules out the formation of such singularities when they are created through the gravitational collapse of realistic matter. This is supported by numerical simulations. Due to the relatively large strength of the electromagnetic force, black holes forming from the collapse of stars are expected to retain the nearly neutral charge of the star. Rotation, however, is expected to be a common feature of compact objects. The black hole candidate binary X-ray source GRS 1915 + 105 appears to have an angular momentum near the maximum allowed value. Black holes are commonly classified according to the mass independent of angular momentum J, or electric charge Q. The size of a black hole, as determined by the radius of the event horizon, or Schwarzschild radius, is roughly proportional to the mass m through r underscore mathrm frac squared approx 2.95 fracm underscore mathrm tilde mathrm math greater than, where rsh is the Schwarzschild radius and msun is the mass of the Sun. This relation is exact only for black holes with zero charge and angular momentum. For more general black holes it can differ up to a factor of 2. Event horizon. The defining feature of a black hole is the appearance of an event horizon, a boundary in space-time through which matter and light can only pass inward towards the mass of the black hole. Nothing, not even light, can escape from inside the event horizon. The event horizon is referred to as such because if an event occurs within the boundary, information from that event cannot reach an outside observer, making it impossible to determine if such an event occurred. As predicted by general relativity, the presence of a mass deforms spacetime in such a way that the paths taken by particles bent towards the mass at the event horizon of a black hole. This deformation becomes so strong that there are no paths that lead the way from the black hole to a distant observer. Clocks near a black hole appear to tick more slowly than those further away from the black hole. Due to this effect, known as gravitational time dilation, an object falling into a black hole appears to slow as it approaches the event horizon, taking an infinite time to reach it. At the same time, all processes on this object slow down from the viewpoint of a fixed outside observer, causing any light emitted by the object to appear redder and dimmer, an effect known as gravitational redshift. Eventually, the falling object becomes so dim that it can no longer be seen. On the other hand, indestructible observers falling into a black hole do not notice any of these effects as they cross the event horizon, according to their own clocks, which appear to them to tick normally. They cross the event horizon after a finite time without noting any singular behavior. It is impossible to determine the location of the event horizon from local observations. The shape of the event horizon of a black hole is always approximately spherical. For non-rotating black holes, the geometry of the event horizon is precisely spherical, while for rotating black holes the sphere is oblate. Singularity. At the center of a black hole, as described by general relativity, lies a gravitational singularity, a region where the spacetime curvature becomes infinite. For a non-rotating black hole, this region takes the shape of a single point, and for a rotating black hole, it is smeared out to form a ring singularity that lies in the plane of rotation. In both cases, the singular region has zero volume. It can also be shown that the singular region contains all the mass of the black hole solution. The singular region can thus be thought of as having infinite density. Observers falling into a Schwarzschild black hole cannot avoid being carried into the singularity. Once they cross the event horizon, they can prolong the experience by accelerating away to slow their descent, but only up to a limit. After attaining a certain ideal velocity, it is best to free fall the rest of the way. When they reach the singularity, they are crushed to infinite density and the mass is added to the total of the black hole. Before that happens, they will have been torn apart by the growing tidal forces in a process sometimes referred to as spaghettification or the noodle effect. In the case of a charged or rotating black hole, it is possible to avoid the singularity. Extending these solutions as far as possible reveals the hypothetical possibility of exiting the black hole into a different spacetime with the black hole acting as a wormhole. The possibility of traveling to another universe is, however, only theoretical, since any perturbation would destroy this possibility. It also appears to be possible to follow closed time-like curves around the Kerr singularity, which lead to problems with causality like the grandfather paradox. It is expected that none of these peculiar effects would survive in a proper quantum treatment of rotating and charged black holes. The appearance of singularities in general relativity is commonly perceived as signaling the breakdown of the theory. This breakdown, however, is expected. It occurs in a situation where quantum effects should describe these actions, due to the extremely high density and therefore particle interactions. To date, it has not been possible to combine quantum and gravitational effects into a single theory, although there exist attempts to formulate such a theory of quantum gravity. It is generally expected that such a theory will not feature any singularities. Photon sphere. The photon sphere is a spherical boundary of zero thickness in which photons that move on tangents to that sphere would be trapped in a circular orbit about the black hole. For non-rotating black holes, the photon sphere has a radius 1.5 times the Schwarzschild radius. Their orbits would be dynamically unstable, hence any small perturbation, such as a particle of infalling matter, would cause an instability that would grow over time, either setting the photon on an outward trajectory causing it to escape the black hole, or on an inward spiral where it would eventually cross the event horizon. While light can still escape from the photon sphere, any light that crosses the photon sphere on an inbound trajectory will be captured by the black hole. Hence any light that reaches an outside observer from the photon sphere must have been emitted by objects between the photon sphere and the event horizon. Other compact objects, such as neutron stars, can also have photon spheres. This follows from the fact that the gravitational field external to a spherically symmetric object is governed by the Schwarzschild metric, which depends only on the object's mass rather than the radius of the object. Hence any object whose radius shrinks to smaller than 1.5 times the Schwarzschild radius will have a photon sphere. Ergosphere. Rotating black holes are surrounded by a region of spacetime in which it is impossible to stand still, called the ergosphere. This is the result of a process known as frame dragging. General relativity predicts that any rotating mass will tend to slightly drag along the spacetime immediately surrounding it. Any object near the rotating mass will tend to start moving in the direction of rotation. For a rotating black hole, this effect is so strong near the event horizon that an object would have to move faster than the speed of light in the opposite direction to just stand still. The ergosphere of a black hole is a volume whose inner boundary is the black hole's oblate spheroid event horizon and a pumpkin-shaped outer boundary, which coincides with the event horizon at the poles, but noticeably wider around the equator. The outer boundary is sometimes called the ergosurface. Objects and radiation can escape normally from the ergosphere. Through the Penrose process, objects can emerge from the ergosphere with more energy than they entered. This energy is taken from the rotational energy of the black hole, causing the latter to slow. In a most stable circular orbit (ISCO), in Newtonian gravity, test particles can stably orbit at arbitrary distances from a central object. In general relativity, however, there exists an innermost stable circular orbit, inside of which any infinitesimal perturbations to a circular orbit will lead to in-spiral into the black hole. The location of the ISCO depends on the spin of the black hole. In the case of a Schwarzschild black hole is r_3, r_s frac squared, and decreases with increasing spin. Formation and evolution. Considering the exotic nature of black holes, it may be natural to question if such bizarre objects could exist in nature, or to suggest that they are merely pathological solutions to Einstein's equations. Einstein himself wrongly thought that black holes would not form, because he held that the angular momentum of collapsing particles would stabilize the motion at some radius. This led the general relativity community to dismiss all results to the contrary. For many years, however, a minority of relativists continued to contend that black holes were physical objects, and by the end of the 1960s, they had persuaded the majority of researchers in the field that there is no obstacle to the formation of an event horizon. Once an event horizon forms, Penrose proved, general relativity without quantum mechanics requires that a singularity will form within. Shortly afterwards, Hawking showed that many cosmological solutions that describe the Big Bang have singularities without scalar fields or other exotic matter. The Kerr solution, the Noether theorem, and the laws of black hole thermodynamics showed that the physical properties of black holes were simple and comprehensible, making them respectable subjects for research. The primary formation process for black holes is expected to be the gravitational collapse of heavy objects such as stars. But there are also more exotic processes that can lead to the production of black holes. Gravitational collapse. Gravitational collapse occurs when an object's internal pressure is insufficient to resist the object's own gravity. For stars, this usually occurs either because a star has too little fuel left to maintain its temperature through stellar nucleosynthesis, or because a star that would have been stable receives extra matter in a way that does not raise its core temperature. In either case, the star's temperature is no longer high enough to prevent it from collapsing under its own weight. The collapse may be stopped by the degeneracy pressure of the star's constituents, allowing the condensation of matter into an exotic denser state. The result is one of the various types of compact star. The type of compact star formed depends on the mass of the remnant of the original star left after the outer layers have been blown away. Such explosions and pulsations lead to planetary nebula. This mass can be substantially less than the original star. Remnants exceeding are produced by stars that were over before the collapse. If the mass of the remnant exceeds about, either because the original star was very heavy or because the remnant collected additional mass through accretion of matter, even the degeneracy pressure of neutrons is insufficient to stop the collapse. No known mechanism is powerful enough to stop the implosion, and the object will inevitably collapse to form a black hole. The gravitational collapse of heavy stars is assumed to be responsible for the formation of stellar mass black holes. Star formation in the early universe may have resulted in very massive stars, which upon their collapse would have produced black holes of up to. These black holes could be the seeds of the supermassive black holes found in the centers of most galaxies. It has further been suggested that supermassive black holes with typical masses of tilde could have formed from the direct collapse of gas clouds in the young universe. Some candidates for such objects have been found in observations of the young universe. While most of the energy released during gravitational collapse is emitted very quickly, an outside observer does not actually see the end of this process, even though the collapse takes a finite amount of time. From the reference frame of infalling matter, A distant observer would see the infalling material slow and halt just above the event horizon, due to gravitational time dilation. Light from the collapsing material takes longer and longer to reach the observer, with the light emitted just before the event horizon forms delayed an infinite amount of time. Thus the external observer never sees the formation of the event horizon. Instead, the collapsing material seems to become dimmer and increasingly redshifted, eventually fading away. Thank you for watching. Brought to you by Wikividi Documentaries. Please like and subscribe below. Please like and subscribe below.